Hello everybody. So in the last class we were discussing about the DC generator, mainly about the structure of the generator, the way the commutator poles are segmented, the way the brushes are positioned in the neutral zone, so as to get an output that is ripple free, that is containing as little ripple as possible. Today we continue the discussion on the DC generator and complete the equation for the generated E.M.F across the brushes. We saw in the last class that the generated E.M.F across the brushes, e.g., is given by N phi z by 60. This is the volts, and we also did a small example to consolidate this understanding of this particular equation. Now here N is the RPM of the rotor, the armature, phi is the flux per pole, z is the total number of conductors in the armature. Here we have always been assuming that there is just one set of north and south poles, and in between you have the armature, and inside we also draw the segmented commutator. So we have the commutator which is doing the job of rectification, and of course the brushes placed in the neutral zone. So for such a configuration, so you could have n slots. So if there are n slots on the armature, there will be n coils, and if there are n coils, there will be n segments on the commutator. Now we could have multiple pole pairs. We see that here you have one pole pair, one north-south pole pair. Let us say we place the pole pairs north, south, north, south, north, south. Alternately, poles are placed of opposite polarity, but the pole pairs are diametrically opposite, meaning this is one set of pole pair, this is another set of pole pair, and we have another set of pole pair here. So you have three pole pairs arranged in this fashion. So these pole pairs and of course here you are going to have the commutator with the segments and the brushes placed appropriately in the neutral zone. You see the neutral zones will be always in between, at the midpoint in between two poles of opposite polarity. So it is always, that is where you will get zero voltage induced onto the coils, and therefore the brushes have to be placed in the neutral zone. Now here you have three pole pairs, and therefore to incorporate also the finite number of pole pairs, which need not be always one, the modified equation for the generated E.M.F, e.g., is pole pairs P. P is the number of pole pairs N, phi, Z. All others mean the same quantities as we had described earlier. So, P will be the number of pole pairs. As poles do not exist independently, they always exist in pairs. You can't have a pure north pole or a pure south pole. We normally talk in terms of pole pairs, or if you want to talk in terms of poles, they will always be even numbers, multiples of 2. So, the number of pole pairs, N is the speed of rotation in RPM, phi is the flux in Webers per pole. Per pole means per pole pair, and Z is the total number of conductors in the armature. So, Z is the total number of conductors in the armature. So, this would give you the induced EMF of a DC machine, a DC generator, which has P number of pole pairs, N is the speed of the rotation, phi is the flux per pole, and Z is the total number of conductors in the armature. Now, there is one important aspect that we need to study. We have the energy coming from the mechanical domain, goes into the magnetic domain, and then finally comes out through the electrical domain by means of the brushes, and this comes out as the induced voltage E.g. So, one is applying a torque here. Now, if one loads here, that loading effect on the electrical side should percolate back and get reflected on the mechanical side, so that you draw more energy. So, there should be any load here should reflect as a reverse torque here, such that the prime mover, whatever is moving the mechanical shaft, should now apply that extra torque to overcome that load and still rotate it at the same RPM, so that you get the same induced EMF E.g. So, this loading effect here in effect has made the prime mover, whichever is driving this shaft, to now give more energy to the mechanical shaft to supply the energy to the load. So, this is how in any energy conversion process, there should always be a loading effect which should percolate back. How does this happen? How does this loading effect back onto the shaft happen in a DC machine? Because that is an important thing to understand, and that is happening by means of what is called the Lorentz force. So, we saw that in the DC machine there are two important equations that you need to remember. One is the Faraday's law of electromagnetics, the alternative equation, which is E is equal to BLV. The other is the Lorentz force acting on the conductor. So, what is it? So, let us take a north pole and a south pole. And let there be flux lines. So, these are flux lines RB, which is equal to phi by A. Now here let us place a conductor and let a current flow through the conductor, and we are passing a current through the conductor, and that is going into the board. The direction of the current is going which is now we saw that when there is a current flowing through the conductor, by the right hand rule there is going to be a magnetic field set up around the conductor. So that magnetic field is, as it is going in by the right hand rule, if it goes in, then the fingers will encircle in a clockwise direction. That is, it is going into the board, the fingers are encircling in a clockwise direction. So which means the field will be in a clockwise fashion. So we have the field due to the current I, and that is in clockwise direction. So now you see what's happening. The field produced due to the current, the orange ones which are shown, and the field of the permanent magnet, they both are going to, the field is aiding, the field produced by the current in the conductor is aiding the north-south field, and below the conductor, the field produced by the conductor, current flowing in the conductor, is against the magnetic field of the north-south conductor. So here it is against, and here it is aiding. So equivalently, we will land up with a field distribution. So there is a current I flowing here, and because of the I flowing we had those things. Now the field on the bottom side of the conductor, it tries to cancel. So the field is weak and the field is strong on the top of the conductor. Whereas it is weak on this side. So this field is acting now like a rubber band which is trying to push the conductor down. So there is a force which pushes down because of the current I which is flowing through the conductor I. Now this force is called the Lorentz force. Now there is an interesting rule, a memory tip for you to remember the direction of the force. If the thumb is pointing, take again the right hand, always the right hand. If the thumb is pointing in the direction of the current flow in the conductor, and the forefinger or the index finger is pointing in the direction of the north-south magnetic field, then the middle finger, which is at right angles to both the thumb and the forefinger, you see that all three fingers form the three coordinates of a system, and each is orthogonal to the other. So the middle finger now points in the direction of the force. So if you point the thumb in the direction of the current and the forefinger extended, which is now orthogonal to the thumb, pointing in the direction of the applied field, which is the north-south magnetic field, then the middle finger, which is also orthogonal to the other two fingers, will now point in the direction of the force, in the direction of the Lorentz force, and that is the direction in which the conductor will tend to move. So, what is the value of this Lorentz force? The Lorentz force F is given by a very simple equation, B into I into L, where B is the flux density of the magnetic field, and in this case it is the flux density of the north-south magnetic field that is being applied, and which is this. And then I is the current flowing through the conductor. Which in this case is this, the current flowing through the conductor, and L is the length of the conductor So, this gives the force newtons on a conductor which is placed in a magnetic field B of length L, carrying a current I through it. So, the direction of the force, as I said, you use the right hand rule to find out the direction of the force. So, now let us apply this Lorentz force principle to the DC machine. So, we have the DC machine with a north pole and a south pole as shown here. Now, let us have the armature or the rotor, as one may call, circular fashion like this. Now, there are coils, and we will represent the coils in terms of circular conductors here, in this fashion. So on, like that. So, at a given instant of time, now this is the neutral zone, this is the neutral zone. There is no voltage being induced on this conductor and this conductor, so there is no current flow. Now, let us say there is a current flow in this conductor, and let us say it is going into the board, and because it is away from the neutral zone, there is going to be a current flowing in here. All these will be in the same direction with magnitudes varying. The one which is nearest to the south pole will have the largest magnitude. So, again this conductor is going to have zero current because it is in the neutral zone, and then here the direction will be opposite, coming out of the board with varying magnitudes. The one nearest the north pole is going to be having the largest magnitude of the induced current. Now, these are the armature conductors. Now, these armature conductors are connected to the commutators, isn't it? So, the armature conductors are connected to the commutators, and through the brushes through the brushes, we see that the external circuit is connected. Now, we apply a load to the external circuit, which has a voltage induced Eg due to the generator action, and there is a current that flows through the external load. Okay. So, this is a current I and there is a load RL. Now, this I is going to flow through the respective conductors, that is through the armature. Now, if we take a particular, conductor, let us say this particular conductor which I am showing here with the cursor, now that is flowing into the board. Now, there is a magnetic field which is being applied in this direction, and therefore, there has to be a force which is in this direction. You have the force. Likewise, this conductor will have a force in this direction. This conductor will have a force in this direction. All these forces will add up. Each conductor will apply a force in this direction, downwards. Okay. Now, the current is going, the current is coming out, and by again applying the right hand rule, you will see that the force will be applied. It will be in direction pointing up, and therefore, they all will be aiding. The forces on each current will be aiding. So, these are the forces, the Lorentz force due to the load current which is flowing through the armature. Now, this force is applying a torque on the shaft, and the prime mover has to overcome this shaft, which means now the rotation is in this direction, anti-clockwise. This is the rotation of armature, but the loading effect is giving a rotating torque which is in the clockwise direction. So, an extra power has to be generated by the primary, which will try to force against this clockwise loading effect torque, such that the armature continues to rotate in the speed. So, thereby it draws more energy from the prime mover and dumps it to the electrical side. This is the energy conversion process on loading. Okay. So, this is how any load gets reflected onto the mechanical shaft and thereby acts as a load on the prime mover.